Hello and welcome to this video tutorial. In part 7 of this video tutorial, we're going to be looking at graphing. Sometimes it will be linear, straight line. Sometimes it'll be nonlinear, some sort of curve. First thing we need to do is take our values and do 3 things to construct our scale. So the first thing we need, first thing we should do is title and label our axes. So let's actually start there. We're plotting velocity on the y-axis versus time on the x-axis. So our title is going to be velocity versus time. Let's put velocity in meters per second on the y-axis, time in seconds on the x-axis. So the first thing we do is title, label. The first thing we should do as a scale and putting together our scale, we are going to put together 3 parts. One, we want to set up our range. Range means we go from a number 0 to some number slightly higher than our highest data point. Okay, so range, we're going from 0 to a number higher, slightly higher than our highest data point. 2, we got to set up our scale. What numbers are we going to go by? Ones, we're going to go by 1s, 5s, 10s, 20s, 50s. Are we going to go by 0.1s? What numbers are we going to go by? Got to come up with your scale. And then finally, the interval you choose. The interval is the number of boxes you skip to go up your scale, okay, or go over on the x-axis on your scale. So let's start with the velocity, the y-axis. I got to go up to 225. Now, I counted these boxes, and let me see. Let me just count them again. So we have 5, 10, 30. Kind of just grouping them off in 5 makes it easier to count them. Okay, so that looks like 42. 5, 10, 15, 20, 25, 30, 35, 40. Got 42 boxes up. And then same thing across the bottom. I have 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 66. So what we're going to do is we're going to first plot the range. So now the range, we're going from 0 to a number slightly higher than 225. So the range is 0 to a number slightly higher than 225. So we can try and go by 50s. That means every box would be 10. Now, it won't go all the way up, but what it does do is it gets at least half the graph, which is more than enough to be accurate. And then on the x-axis for time, we can go by seconds. So I can go 1, 2, 3, 4, 5, 6. Nope, not enough. Can't do that. So I need to go like something like this. Every 5 boxes, maybe 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 seconds. So at this point, go ahead and plot your data point. What I want you to do right now is go ahead and pause the video, plot your data, and let's go ahead and compare notes on your video in just a second. Okay, so the first one we're going to plot is go over 1 second and go up to 32. So over 1 second, up 32 would be about right there. Then we're going to go over 2 seconds, up 63. 63. Then we're going to go over to 3 seconds and up almost 100 to 97. That would be about right there. Then we're going to go over to 4 seconds and up almost 130 to 129. So 4 seconds, 110, 120, 130, 129 would be just a little bit less than that right there. Okay, I'm going to go 5 over to 5 seconds and to 159, which is almost to 160. So we're over here, 159, 160 puts it almost right there. Okay, and then we're going over 6 seconds, which is 5 over more, and then up to 192. That would put it right there. Then finally, you're going to go over 5 more, which is 7 seconds, and up to 225. So there's 210, 220, 225, puts it right halfway between 2 and 250. Okay, and we have a nice linear progression of data. Go ahead and draw a best fit line through that. Make sure it is a straight line like I'm doing. Okay. Now, what is the shape of this graph? Well, clearly it's a line. Okay, so the graph is linear. What does the area under the curve represent? Well, the area under the curve, if you can see, would be this triangle that I'm shading out right here. Okay, that's the area underneath this thing. Now, think about it, ladies and gentlemen. When you're finding the area of a triangle, you're multiplying 1/2 base times height, meaning you're multiplying the sides. Well, the sides would be the axes. So when we are finding area, you're actually multiplying the axes together. So that would be, in this case, the area would be one axis, a unit. So multiply the units. It would be meters per second times, in this case, seconds. You can see that cancels, giving you meters. So what does meters represent? How far, or the displacement of this object, how far it went in a particular direction. Okay, what is the relationship between these variables? Well, this, ladies and gentlemen, is what is called a direct relationship. Direct relationships are linear, and they start from the origin 0, 0. What is the velocity after 6.5 seconds? Well, what I'm gonna do is I'm gonna go 6.5 seconds, and I'm gonna go up to the graph, and then from the graph, I'm gonna go over like this. So here's 6.5 seconds right on the graph. And then I'm gonna go over, and I'm gonna estimate that to be about, looks like a little less than 210 meters per second. So I'm gonna say the velocity is about maybe 208, so a little less. Okay, and then similarly, to get the speed, says when, that means what time, is the speed at 115. So I'm gonna go to 115 on here, go over the graph, and then down. So 115 would be exactly here. Okay, go over to the graph. Okay, and then go straight down. That puts it right here at every mark is essentially 0.2, so that would be 3.6 seconds. So yes, we have to be able to find slope. Yes, we have to be able to calculate area. But one of the fundamental ideas of graphing is to also be able to take a particular information on a graph and just read the information off the graph. That's also very important. Okay, moving on to question number 39, our second graph. What we're looking at here is we are looking at graphing f, which is the frequency of a wave, and lambda, which is the wavelength of the wave. We're going to make this the independent variable on the x and this the dependent variable on the y. So we're going to be plotting lambda versus frequency. Okay. Now, again, just like we've been doing, we've got to come up with our range. We got to come up with our scale and our interval of boxes that we're going to skip to do this. So if you look, my largest lambda, my largest wavelength is 2,000. So I got to get up pretty high to do that. So I'm thinking, it's the same number of boxes going up. It's about 40 something boxes going up. So I can probably go at a rate of maybe 1, 2, 3, 4, 500. Go every couple boxes is 100. 6, 7, 8, 9, 10, right? That would be 1,000. That seems to do the job, and that would get me up to 2,000. So 1, 2, 3, 4, 5, that's 1,500. And then 1, 2, 3, 4, 5, that's 2,000. So that's perfect. All right, and then the largest frequency you can see is 900. So similarly, I'm going to go ahead and try and skip maybe about 5 boxes along the way. There's 100, 200, 300, 400, 500. Okay, 600. Whoops, I didn't do that very carefully. Let me try that again. So that's 200, 300, 400. There's 500. 6, 7, 8, 9, 10. That's 600, 700, 800, 900, 1,000. Okay, so something like that. Okay, want to go ahead and mark it off. We're going by hundreds, right? At an interval of about 5 boxes for every 100. That means every box would be 20, say 20 hertz going across the side. So let's plot. Our first one is we're going over, okay, 150 and up to 2,000. So here's 100, here is 200, 150 is right in the middle. And you're going to go all the way up to 2,000. Go all the way up right there. And make a dot. There's your first dot. Okay. A second one, we're going to go over 200, up 1,500. So over 2, up 15. Okay, there's 1,500. Okay, the next one we're going to go 300 and up 1,000. So 300 up 1,000. That would be right there. Okay, then we're going to go over 500 and then up 600. Okay, so you can see 500 and 500 would be here. 500, 600 would be right there. Okay, then we're going to go over 600, up 500. That would be here and then up to there. See the graph starting to level off a little bit. It's decreasing. Okay, and then our final plot is we're going to go over 900 and up a third of the way, which is about 333. So over 1,000, 300 is here. Okay, 350, 333, so I kind of like over there. So now we're going to just go ahead and draw a best fit curve through this. Okay, might look something like this. And you can see that as frequency gets bigger, remember frequency is on the x-axis in hertz, the wavelength gets smaller. Okay, what shape does this graph? This is a decreasing curve, right? Sometimes this is referred to as an inverse graph or an inverse model. Okay, what does the area under the curve represent? Well, the area here, this might be a little bit hard to understand because the units of meters times hertz doesn't really make a whole lot of sense, but the area under this one would essentially be wavelength times frequency, which is v, or the speed of the wave. I know that seems like a random idea here, but yeah, frequency times wavelength is the speed of the wave. What is the relationship between those variables? Well, lambda, the wavelength, is inversely related, meaning as one goes up, the other goes down to frequency. What is the wavelength when the frequency is 450 hertz? Okay, so 450, I go here, 450 is right exactly here. I go up to the graph, then I go over. And then I just go ahead and estimate what that is. 600 and not quite 50, maybe pretty close to 633. All right, wavelength somewhere around 633, 635, 640 maybe nanometers. Oh, meters. Okay. What is the frequency when the wavelength is 225? So 2, you have 2 is here, 3 is here, 250 is in the middle, 225 is halfway. And that's pretty hard to tell because it doesn't really hit the graph per se. But what we could kind of do is just sort of guesstimate it according to the model in terms of how it is, and it's getting up there in terms of frequency. So I it's roughly, you can see right now at 1,000. I mean, to get down there, I mean, here would be 1,100, 1,200, 1,300. I mean, maybe 14 or 1,500, right? Somewhere around there. 1,400 to 1,500 hertz would be roughly about what that is. It's kind of hard to tell exactly because we didn't extend the graph far enough. Okay, now the next questions pertain to graphing ideas, but we're not using a graph. We're just looking at some graphing ideas. So in number 45, okay, if you wanted to graph the period of a pendulum, t equals 2 pi times the square root of L, the length of the pendulum, over g, gravity. In order to show that the period does not depend on the mass, what would you have to graph? So we would graph period versus the mass. Okay, and if we did this to show period, which is t, period is the time it takes a pendulum to swing back and forth, is independent of mass, how much is on the end of the pendulum, the graph would show a flat horizontal line. Okay, number 46, okay, what would we do? What shape would the above, what would be the shape of that graph? Well, it's a square root function. If you look at that, it's a square root function. So t, well, actually, I'm sorry, the graph of period versus the mass, excuse me, not this right here, period. So the graph of period t versus the mass would be horizontal because it would show no dependence. It would show independence. So when it's flat across, one variable does not depend on the other. So it would be horizontal. How would you show the relationship between period and the acceleration due to gravity, which is little g? So for that one, what we would do is we would graph a couple of things. We would either, okay, look at your variables here. We can see that t, the period, is proportional to the square root of 1 over g. So we could either graph the period versus the square root of 1 over g, or you could square both sides and graph the period squared versus 1 over g. So by graphing these, you would see how the period depends on gravity pulling on the pendulum. Okay, what would the shape of that graph be? The graph would be linear when you did this. Okay, I hope you felt this video tutorial to be helpful in some way. Thank you. That is all.